Bismillahirrahmanirrahim. In this lecture we will discuss two things. One thing is that we will check whether an as-such type surface wave can exist or not, and secondly we will see that we will derive the dispersion relation for an isotropic plate. For an as-such surface wave, we know that polarization must be in third direction for a propagation in x1 x2 plane, for propagation vector in x1 x2 plane. So we have first two components u1 and u2 0, because of the first two components of polarization vector 0 0, u1 u2 will be 0. So we have only u3 for SH wave, as we were discussing earlier in our previous lectures. No, this is the form of the SH wave that we have taken this u3 component in the form of SH wave. That this is telling that we have SH wave, and this is that it is moving in the x1 direction. Let's see whether we have actually SH wave as surface wave or not. No, we will see this thing. Equation of motion, you know that this is the equation of motion for the displacement. We use the displacement component, and this equation shows that we have the half space filled with the isotropic material, and there are three components. There are three components with the help of this equation u1, u2, and u3. That this is the vector form of the equation, and this contains exactly three sub equations 1, 2, and 3 for u1, u2, and 3. As we have only u3, u1, u2 are 0, so we need only third equation from here. So this can be written for u3 as u3 and divergence of u. You know that u1 and u2 0, so partial u1 partial x1 and partial u2 partial x2 they both will be 0, and we have only partial u3 partial x3, gradient of this partial u3 partial x3. And on right hand side we have density u3 double dot means that we are taking derivative with respect to time. So this would also be 0, because our u3 is independent of x3. You can see that we have no x3 in the equation number 1, so this would be equal to 0. So we are left with only this form, equation number 2. And as we have done earlier, first we will find small b, then we will go to the boundary conditions. Let's see how can we find this small b. By using, we know that u3 is given by equation 1, so use that u3 which is given in equation 1. In equation number 2 we have this thing, mu minus k square a, this plus b square a, and on right hand side minus rho k square c square a. So as we have supposed that we have the u3, so it means that a is not equal to 0, is not equal to 0, because we are taking u3 as non-zero. If a is 0, then u3 is 0, so we have a3 not equal to 0. So from here you can have your b as minus k square plus b square equal to this. Simplify this, then we can write your b. This is as in the previous lecture. B is equal to k times into 1 minus c square or ct square. This is equation number 3. Now from the boundary conditions, what we have, we know that if we will have to apply the boundary conditions, then we have these three components equal to 0. T21, T22, T23 equals to 0. For x2 is equal to 0, at x2 is equal to 0, and this is the stress strain equation. T21 is 0 because u1 u2 0, T22 0 because u1 u2 is 0, and u3 is independent of x3, and we are left with only T23. This is here like this, and this would be equal to 0, and we have only this. So take the partial derivative of u3 with respect to x2, we have this thing, and we know that T23 is equal to 0 at x2 is equal to 0, so this would be equal to 0. So from here we can write BA equals to 0. So this thing is telling that either B is 0 or A is 0. So let's see what happens when small b is 0 and what happens when capital A equals to 0. When small b is 0, then we have no surface wave. Then the factor which is giving the characteristic of surface wave equals to 1, so we have no surface wave, and when A is 0 then we have no wave. So it means that we have no SH wave as surface wave. So what is our conclusion? Our conclusion is that an SH type surface wave cannot exist. So let's go to the dispersion relation for an isotropic plate. So far we have discussed the half space motion of wave in half space. Now you know that in half space we have one boundary or interface between two joint half spaces, and now we will see the motion in layer. Layer means that we have two boundaries and we have finite thickness, but it will be infinite in plane directions like this. We have two boundaries. This is finite thickness 2h, and by using our previous result we know we can say that wave is reflecting back and forth in this layer and move in the direction of this layer. So as this layer is guiding the wave to move along the direction, so we can say that this layer as wave guide. With the help of the name we know that what does this wave guide mean, that which guides the wave is called wave guide, that how it has to move and in which direction it will have to move. So we have basically two types of wave guide. Two types mean two types of geometry to discuss as wave guide. One is plate geometry, in which we have Cartesian rectangular coordinates, and other is cylinder, other wave guide in the form of a cylinder, in which we will take cylindrical coordinates. This is the plate-like structure. This is the plane x1, x2, and this is the thickness, and it is infinite on this direction, left and right. In this direction it is infinite, and finite in this direction, plus h or minus h, so 2h total thickness. This is the form of the wave guide as cylinder. Diameter is finite, but it is infinite in this direction, and then r and theta, they are the coordinates. So we need r, theta, z for the discussion of wave guide in the form of cylinder. But here we will discuss the wave guide in the form of plate. Then we have written here isotropic plate. It means that plate is made of we are using the isotropic material for that plate. So we have plate-like structure, and that the material is isotropic. So that is why we have written here isotropic plate, that we are going to discuss or derive the dispersion relation for an isotropic plate. Now, what does this dispersion relation mean? This dispersion relation is the basic relation between the phase velocity c and wave number k. So at the end we will have a relation between c and k. C phase velocity and k is wave number of the wave. So from there we will have relation at the end. So that relation is called dispersion relation, sometimes called frequency equation. Now we will consider this motion in x1, x2 plane. So u3 will be 0 identically. So we have only u1 and u2, but they would be independent of x3 because we are taking x1, x2. So u1 and u2, their partial derivative will be independent of x3. So their partial derivative will be equal to 0. No, we will write here, we will have use only boundary conditions to find the dispersion relation. So to apply the boundary condition we need, because you know that when we have free boundary we must have that we will suppose that our stresses vanish at the boundary of the plate, either above or below, either at x2 is equal to plus h or x2 is equal to minus h. The boundary so stresses will be equal to 0. So we need, and when we use the stress strain equation, there exist u displacement components, u1, u2, u3. So we need u1, u2, u3. Let's take u in this form. You have already studied this form, del phi plus curl of psi. This is vector scalar potential and this is vector potential. As you can write, this is gradient of phi and this is curl of psi. So u1 for curl phi 1, first component of gradient of phi plus first component of curl of psi. Now first component will be partial phi partial x1 of this, and this is the first component partial psi 3 partial x2 minus partial psi 2 partial x3. As we are independent of x3, so this term will be equal to 0, or you can say that to have the third component of this equal to 0, we need psi 1 psi 2 equals to 0. So what is u2 for second component plus second component. For second component of this is partial phi minus x2 partial phi partial x2 minus, for second component of this would be partial psi 3 partial x1 again minus partial psi 1 partial x3 will be equal to 0. So we have u2 partial phi partial x2 minus partial psi 3 partial x1. As we have no psi 1 psi 2, so we can ignore this subscript 3. So we will drop this subscript 3 and we have this u1 and u2, where phi is the scalar potential and psi, and what is psi? Psi is basically the third component of the vector potential, in which we have ignored this 3, so there is no 3 written. No, you know that these are the two displacement equations which has been satisfied by phi and psi. You have derived these two equations. Let us take the solution in this form. You have taken the solution like in u1 for u1 and u2 and Rayleigh surface wave, in which you have written this exponential, and this is telling that where wave is moving in x1 direction, and here we have at that time e power minus bx2, but here we have written this unknown function of x2. We will find this function. We have multiplied this wave number k inside, so we have kx1 minus kct, and here kc is omega, and this is phi. Now as we are saying that these are the solution of 1 and 2, so these will must satisfy these 1 and 2. So we have, first we will put phi, we have this equation, simplify it, we have this differential equation, second order differential equation. So we can write this equation, this function, its solution as this in this form, where p square is w square omega square or cl square minus k square. No, this is our function, unknown function, which I have said that we will find this type of function, in which in our Rayleigh surfaces we have a into e power minus bx2. Here we have this form, trigonometric functions, and a1 and a2. When we will find psi, we will have this type of relation b1 b2, where q is this q square is omega square over ct square minus k square. So you can write your u1 u2 in this way by using our phi and psi in u1 and u2. Your u1 and u2 will become in this way. Then you can write your Tij equals to this stress strain equation, lambda delta ij skk plus 2 mu delta ij. T23 will be equal to 0 because u3 is 0 and this term is 0 because delta 21, this will be 0 because u3 is 0 and we are independent of x3. This is T21. Simplify a little bit this, take the derivative of u1 with respect to x2, then u2 with respect to x1, we have this thing, and we have T21 this. For T22 we have this, simplify a little bit, we have T2 this. Now we have basically two equations, T21 and T22, but we have four unknowns, A1, A1, A2, B1, B2. As in the Rayleigh wave equation, we have at that time four unknowns, Then we have converted those four unknowns to two unknowns with the help of some conditions, with the help of some reasons. Similarly, here again we will split these four to 2. How we will split these 4 to 2? Like this. As u1 and u2 contains elementary functions, elementary trigonometric functions, sine and cos. So for displacement, here we will talk about symmetric motion and anti-symmetric motion, and with the help of this symmetric and anti-symmetric motion we will split these 4 into 2. These 4 constant unknowns to 2 unknowns. For symmetric we have 2 unknowns, and for anti-symmetric then we will have again 2 unknowns, that we can solve these 2 separately. So we will have 2 types of result, anti-symmetric or symmetric. So how we will do this? In x1 direction, motion is symmetric with respect to x2 is equal to 0 if u1 contains cosine, and in the x2 direction it is symmetric when u2 contains sine. So it means that when our u1 contains cosine, means that there is no sine in u1, then it will be symmetric, and u2 it contains sine. Now when this will happen? When we will put the form of phi and psi as that, when we will use these phi and psi in u1 we have cosines, and in u2 we have sines. How we can do this? Like this. For symmetric modes we have phi in this way, a1 cos px2, and psi in this way, b2 sin qx2. Now use this phi and psi in u1, you will have totally cosines in u1, and use these phi and psi in u2, you will have totally sine in u2. So this corresponds to symmetric modes. So when you have this and phi and psi, so we will have symmetric modes. Now use this phi and psi into t21 and t22. We have this is t21, this is t22. These two are. Now we will use the boundary conditions here. t21 t22 equals 0 at x2 plus minus h. Either you can put plus h or minus h, nothing will make the difference, so you can use plus h or minus h. So at x2 you will use plus h or minus h. So for t21 using plus h you will have this thing, and for t22 using plus h you will have this thing. So we have 2 unknowns, a1 and b2, and 2 equations, so we can use the result. Homogeneous system for non-trivial solution, determinant must be equal to 0, so we have the result. Now I have written this directly. You have to do this, you have to obtain this relation. That's when you will take the determinant equal to 0, and after simplification you will have this, and this is the dispersion relation for symmetric modes. As we have taken phi as psi such that we have u1 contains all cosines and u2 contains all sines, so we have symmetric motion. So corresponding to this we will have this type of symmetric dispersion relation. And when you will use for anti-symmetric modes, here you will be for anti-symmetric modes phi equals to a2 sine and psi equals to b1 cosine. Only in that case u1 will have sines and u2 will have cosines. So again you will repeat this whole process, and at the end you will have this type of relation. This is the anti-symmetric relation and this is the symmetric relation. So from here we will get the symmetric modes, and from here we will get the anti-symmetric modes. So this is the dispersion relation for symmetric modes, and we have taken the isotropic plate. So this will give us the mode spectrum for isotropic plate, and this is the symmetric mode spectrum, and this will give us the anti-symmetric modes for isotropic plate. Here I am using the word lamb. This is basically Horace Lamb is the mathematician which discussed these modes first, and at his name we say that its name is Lamb. Names are Lamb modes. Lamb modes are basically the dispersion curves which we will plot corresponding to these two relations. This is for symmetric and this is for anti-symmetric. Thank you so much. Allah Hafiz.